Physicists estimate that the universe originated roughly 13.7 billion years ago through a mysterious phenomenon commonly referred to as the Big Bang. Although this concept has become a central pillar of modern cosmology, the precise cause or initiating mechanism behind this immense event remains one of the most enduring enigmas in science. Over many years, scientists have thoroughly examined the universe's beginnings and its subsequent evolution. The Big Bang theory has long stood as the predominant explanation for how the universe came into existence, bolstered by extensive observational evidence and robust theoretical frameworks. Contributions from researchers across the globe have strengthened this model, cementing its role as a foundational theory in astrophysics. According to this model, a puzzling form of energy known as dark energy, believed to surpass all the visible matter in the universe in abundance, has been responsible for the universe's continued expansion since its inception. Dark energy is thought to act as a repelling force that counteracts gravity, accelerating the universe's growth. However, as scientific methods and observational technologies have progressed, new findings have started to challenge the long-standing assumptions that once seemed definitive. What was previously considered settled knowledge now appears to be more intricate and less certain. One notable challenge to the Big Bang theory has come from theoretical physicist Michio Kaku, who recently expressed doubts following remarkable data gathered by the James Webb Space Telescope, JWST. This state-of-the-art telescope has identified more than 750 previously unknown galaxies that deviate significantly from the characteristics predicted by prevailing theories. These unexpected discoveries have led scientists to reassess key ideas about how the universe was formed and how it has evolved over time. While the images captured by the JWST are visually stunning, their importance lies in the critical scientific questions they raise. Researchers were especially surprised to find that these newly observed galaxies exhibit properties inconsistent with current models of early cosmic development. Where scientists expected to find young, chaotic galaxies shaped by frequent collisions in the early, turbulent universe, the JWST instead revealed smaller, older, and unusually smooth galaxies. These findings stand in stark contrast to what the Big Bang model had forecasted. As a result, some cosmologists have described this moment as a crisis point, necessitating a re-evaluation of established beliefs. Traditionally, the Big Bang theory posits that the universe emerged from a singularity, a point of infinite density and temperature where all matter and energy were compacted into an incredibly small space. From this singularity, space and time began, and the universe started to expand. The inflationary model, a refinement of the original theory, suggests that the universe underwent a brief but tremendous expansion, faster than the speed of light, shortly after the Big Bang. This rapid inflation smoothed out early irregularities and laid the groundwork for the large-scale structure of the cosmos. As the universe expanded and cooled, fundamental particles like protons, neutrons, and electrons formed. Within minutes, a process called nucleosynthesis produced the lightest elements, setting the stage for the eventual formation of atoms, stars, and galaxies. Despite this comprehensive theoretical structure, the JWST's observations diverge sharply. Instead of chaotic, early-stage galaxies, the telescope has recorded ancient galaxies with defined spiral and disk-like shapes, similar to those seen in the modern universe. These well-organized structures directly oppose the idea that early galaxies evolved primarily through violent mergers. If these galaxies had not undergone significant collisions, it becomes difficult to understand how such small systems could have developed into the massive galaxies observed today. Additionally, the maturity and quantity of these galaxies challenge the current timeline for how long galaxy formation was believed to take under the Big Bang framework. Another perplexing result from the JWST involves the apparent size of distant galaxies. Observations show these galaxies to be 2 to 3 times smaller than those previously detected by the Hubble Space Telescope, contradicting theoretical expectations. According to the prevailing model, galaxies observed at great distances, meaning we are seeing them as they were in the early universe, should appear larger due to the denser, more compressed nature of space at that time. However, the opposite has been observed. These galaxies appear smaller and more refined, which conflicts with conventional understandings of cosmic expansion. The structural smoothness of these galaxies also raises critical questions. Based on the Big Bang theory, early galaxies were expected to be clumpy and irregular due to the frequent gravitational interactions and mergers that characterize the young universe. Yet the galaxies observed by JWST are surprisingly smooth and well-formed, challenging the accepted narrative of galaxy evolution. This finding undermines the assumption that galaxies formed hierarchically, where smaller ones gradually merged to form larger systems. The new evidence suggests that galaxies might have formed through different mechanisms or developed much faster than previously assumed. These developments also cast doubt on one of the fundamental tools in cosmology, the concept of redshift. Redshift refers to the stretching of light from distant galaxies toward the red end of the spectrum due to the expansion of the universe. This shift has been used extensively to estimate both the age and distance of celestial objects. JWST, using its advanced infrared filters, analyzes this redshift to determine the properties of ancient galaxies. However, the galaxies it has observed appear significantly older than they should, suggesting that mature systems existed much earlier than the Big Bang model allows. This discrepancy forces a rethinking of the universe's timeline and the processes that led to the formation of stars and galaxies. In addition to these surprises, the way galaxies are distributed in the JWST's images presents another major challenge. The Big Bang theory predicts that as the universe expands, galaxies should become increasingly spread out. Yet the JWST data shows that galaxies are clustered more densely in certain areas than the theory would suggest. This unexpected density hints at the possibility of unknown forces or alternative models of gravity influencing the development of the universe. It implies that cosmic expansion might not be occurring in a uniform way, and that our current understanding of the underlying dynamics may be incomplete. The implications of these observations have sparked vigorous debate among cosmologists. While some researchers remain confident that the Big Bang theory can be adjusted to incorporate these new findings, others believe we may be on the cusp of a paradigm shift in cosmology. Future discoveries could point toward a more profound transformation in how we comprehend the origins and structure of the universe. Regardless of where the evidence ultimately leads, it is clear that the JWST has revolutionized the field by providing a much more detailed view of the early universe than ever before. As scientists continue to analyze the JWST's extensive data, it is becoming apparent that the early universe may have evolved quite differently than previously thought. The presence of ancient, compact, and smooth galaxies challenges long-held ideas and raises new questions about the processes behind cosmic formation. These galaxies lack the disorder expected from high-energy environments and frequent interactions, instead appearing to have formed rapidly through processes that are not yet understood. If further research confirms these findings, it could necessitate major revisions to the core concepts of cosmic expansion, galactic formation, and the overall chronology of the universe. The idea that galaxies formed primarily through hierarchical mergers may need to be replaced or significantly refined. Moreover, the discovery of a high concentration of galaxies in specific regions of space indicates that the early universe may have been more structured and efficient at forming systems than previously believed. This points to potential gaps in our current models, including those involving dark matter and dark energy, which together are thought to make up about 95% of the universe. In conclusion, the James Webb Space Telescope has provided an unprecedented, window into the distant past, offering insights that challenge many of the foundational assumptions of modern cosmology. Its revelations have generated both excitement and discomfort within the scientific community, suggesting that the universe may be far more complex than the Big Bang theory can currently explain. As new images and datasets continue to emerge, cosmologists must confront a growing body of evidence that diverges significantly from established predictions. Ancient galaxies with mature characteristics now suggest that large-scale cosmic structures may have formed earlier and more efficiently than previously believed, prompting a search for new explanations that may one day redefine our understanding of the cosmos.